Hi everyone, welcome to lecture 2.2. It's a follow-on from lecture 2.1, but in this lecture we're looking at reporting data. So what we're going to do is look at how to accurately report summary data. When we're talking about summary data, we're talking about our descriptive data, such as the measures of central tendency, measures of dispersion, and also looking at those relationships and how to display those in terms of numbers. So just on to the learning objectives. So what we're going to do is look at how we calculate and interpret the mean, median and mode. These are our measures of central tendency. And you might ask yourself, why are we looking at calculating these things? Excel can do that very well, or any other package. But what we want to do is look at the actual formula so you understand what numbers go into this formula, how they're calculated, to really understand what the number's showing us. Similarly, we're looking at calculating and interpreting our measures of dispersion. This is our range, our variance, standard deviation, and our coefficient of variation. Lastly, we're looking at measures that tell us about the relationship between two variables, and so we're going to go into a bit of detail about the correlation coefficient. Okay, firstly looking at our measures of central location or measures of central tendency. These relate to summary measures of the centre of a data set. These measures include, as we've said, the mean, median, and mode, with the mean, or commonly called the average, being the most commonly reported measure. We often want to know, for example, the average grade in class, the average age of a group of people, average income, average performance at work, etc. The mean is measured by adding up all the values and dividing by the number of values. You can see this on the slide. So first we've got the sample mean, which is represented by x bar. We have sigma, which means sum, and x, which represents the values. So what we do is we sum the values and divide by n, which represents the sample size. That's lowercase n. The formula for the population mean is similar, however this is represented by the Greek letter mu. And so what we do is we sum all the population values and we divide by uppercase n, which represents the population size. As you can see with the formulas, the mean is sensitive to outliers by the very nature of the calculation, where we're adding all the values together and dividing by the number of values. For this reason, we often report the median when we have outliers in our data. So here's an example to further demonstrate this. Here we have a mean calculation which includes an extreme value or an outlier. What we're doing here is we're working out the mean for salary for this particular company, and you can see the values there, and we've got that outlier for the president being 550,000. So when we calculate a mean by adding up all the values and dividing by 7, the number of values, we get a mean value of 154,286. But looking through the data, this does not really typify the centre of the data set or represent that data set at all very well. So in this case, we would go to the median and use the median as the centre of the data. The median is not affected by outliers as it's simply the middle of the data set. If we have an odd number of data points, it's just that middle value. If we have an even number of data points, what we do is we take the two middle values and average them out. Median's often used when we're reporting house prices. So if we take that same data set in terms of employee salary and we look at the median, what we do is we rank order the data from lowest to highest, and you can see the median or middle value is the 90,000, and this better represents the data than the mean of 154,286, because that median isn't impacted by extreme values. There's no calculation there, it's simply that middle score. Lastly, we've got the mode, and the mode represents the most common value. A data set can have no mode, one mode, which we say unimodal, two modes, which we call bimodal, or more than that, which is multimodal. Again, referring to the salary example, the mode here is 40,000. So the mode can be useful for inventory ordering, for example. You know, you might be running a shoe shop and you're not really interested in the mean shoe size or the median shoe size, but the mode or the most common shoe size is really important so we can order more of those. Lastly, we'll talk about the weighted mean, and the weighted mean is important. This is when some values have more importance than others and thus attract a larger weighting. Here's an example of this. So what you can see here is a student has 3 assessments. The scores are out of 100 for each assessment. In this case, exam 1 and 2 are worth 25% of the final grade, and exam 3 is worth 50%. To calculate the student's average score, we could simply average out the three grades of 60, 70 and 80 and would get an average or a mean of 70%. However, this does not take into account the higher weighting given to exam 3. When applying the weightings, what we do is we multiply 60 by 0.25, 70 by 0.25 and 80 by 0.5. Then adding all those up, we get a weighted average of 72.5, which is the correct answer here. Okay, now when we're moving on to measures of dispersion. So often when we're reporting data, we're reading business reports and so on, often it's only the mean that's reported and nothing else. And this is unfortunate as a lot of information is missing. When we're reporting the mean, it's also important to report the standard deviation so the reader gains an understanding of the spread or dispersion in the data set. Let me give you an example. So say in class you get there's an average score of say 70% on a test and you achieve a 68% and you're thinking, well, I got 68%, the average is 70, I'm fairly close to that, so I'm doing okay. But what if I then told you that the standard deviation is 1? This then shows you that you're 2 standard deviations away from that mean, and you may actually, with a 68%, be the lowest score in the class, have the lowest score in the class. So as you can see, and hopefully this example will remind you of this, but not be your reality, that the importance of standard deviation being reported together with the mean. So what we can see when we're looking at standard deviation is that a mean is one thing, but if you get a large standard deviation, what this is really telling the reader is the data is widely spread out and there's a lot of variability in the data. And in that case, maybe the mean isn't actually very useful. A small standard deviation, on the other hand, tells the reader there is less variability or more agreement and consistency in the data. So maybe the mean is more useful. So now let's look at measures of dispersion. We always start with the range. The range is a really quick way to gain an idea of the spread in a data set. So each night when you watch the news on TV, you're often presented with the range in terms of weather. We're often told the minimum and maximum, and this gives us an idea of how the weather varied during the day, how that temperature varied during the day. So the range is calculated as the maximum value subtract the minimum value. Clearly it's impacted by extreme scores, as these are the actual values used to calculate the range. It's a really simplistic measure, and good as a quick measure of the spread of a data set, but there are better ones. So the variance is a more sophisticated measure of dispersion. It can be measured for the population or the sample. For the sample, it's represented by S squared, and it's calculated by subtracting each value from the mean, squaring these values so that the positive and negative values do not cancel themselves out. Then adding up all the values and dividing by the sample size less 1. You can see this in the formula on the screen. The standard deviation is then calculated as the square root of the variance. The standard deviation is therefore more user-friendly as it's in the same units of your data, whereas the variance is in squared units due to the squaring of the data to avoid that cancelling out effect. For the population data, the symbol used is sigma squared for the variance and sigma for the standard deviation. As you can see, the formula is similar in that each value is subtracted from mu, the population mean, squared so that positive and negative values are not cancelled out, then added up. Lastly, the sum to score is divided by the population size, capital N. Sigma, or the population standard deviation, is the square root of sigma squared, the population variance. Okay, so lastly, I can hear you asking yourself, and a very common question I get in face-to-face classes, why is the sample variance divided by the sample size n minus 1, whereas the population variance is simply divided by the population size, capital N? Well, we could look at a bunch of simulations to demonstrate what I'm about to say, or you could just trust me. The reason is that n take 1 gives us what we call an unbiased estimate of the variance. You can think of it as a bit of a correction factor that produces a sample variance closest to the population variance. If we simply divide by n, we actually underestimate the population variance, and this is known as a biased estimate. Okay, so lastly, many students ask me how we determine a good or bad standard deviation. Well, guess what? There's no such thing. You need to decide for yourself whether the standard deviation or the spread of the data is acceptable. Given the standard deviation is in the units of the data, then there is no hard and fast rules that above or below a certain number is acceptable or unacceptable. One way we can bring this to a common language is by computing a coefficient of variation, or something we call a COV. This is the standard deviation divided by the mean. We normally then multiply this value by 100 to get a percentage. Lastly, we're going to talk about measures that describe the relationship between variables, and these measures are covariance and correlation. We'll also revisit this discussion when we look at regression analysis later on. So a correlation coefficient is a value that describes the strength and direction of the relationship between two variables. The sample correlation coefficient is represented by the lowercase letter r, and the population correlation coefficient is represented by the Greek letter rho, which kind of looks like an italicized lowercase p. Note the correlation coefficients range from -1 to +1. The closer to +1 or -1, the stronger the relationship. The closer to 0 means there is little or no relationship. Here are some scatter plots showing different relationships and the corresponding correlation coefficients. It's important to keep in mind with that correlation coefficient score, as I said on the last slide, this is looking at the strength and direction of the relationship. The strength is represented by the number and the direction is represented by the sign, positive or negative. So firstly, in the top left, we have what we call a perfect positive relationship, which means as one variable increases in value, so too does the other variable. The corresponding correlation coefficient is +1. This is interpreted as a perfect positive relationship. The sign being positive shows that it's a direct relationship, and the 1 shows that it is perfect in terms of the relationship. I should note here that the variable on the vertical or y-axis is often referred to as the dependent variable, that is what we're trying to predict. The horizontal or x-axis normally contains your independent variable or your predictor. The next scatter plot across, i.e. top line middle plot, shows an inverse negative relationship. The correlation coefficient is -1, showing it is a perfect negative relationship. The next scatter plot, top line, far right, shows a moderate to strong positive relationship. The correlation coefficient of +0.7 further demonstrates this. Unfortunately, correlation coefficients only account for linear relationships, and in this case there is a slight curvilinear relationship that perhaps better accounts for the relationship. Please note a linear relationship simply means a straight line relationship. Okay, now looking at the scatter plots on the second line. First, there's a scatter plot showing a moderate negative relationship. As you can see, the data points are more spread out and we no longer have that perfect relationship, but we do actually probably have a more realistic and achievable relationship. The scatter plot in the middle shows no relationship, so as x increases, y does not change. So it doesn't matter how closely clustered the data points are to a flat line, this still indicates no relationship. Lastly, the scatter plot, bottom right, shows no relationship according to the correlation coefficient. As you can see by the scatter plot, a clear and perfect curvilinear relation is evident. That is a perfect negative parabola. This is a clear warning of the importance of always viewing your data as scatter plots, and also that correlation coefficients only account for linear relationships.